everyone. You know what is that, right? About this way.
There we go.
Yes,
This way? Okay, this is a hot drive, right?
Yep.
When I pass it, so you can take a look at it, pass it on. You can open it this way. You can, as you see, you can touch it. This is the read write head. Okay, so you see how it moves back and forth. So the hard drive is rotating all the time, and this one is moving. So when this connection, let's say, is to the controller, so when the controller sends a command, then the read-write head moves toward the inmost track, the outmost track, and when the write track is located, then the information is transferred this way through the controller, from the controller CPU memory and system, okay, or directly to memory. Okay. So you can see that in this one, we have two of them, right? So the read-write head, if you pay attention, you have it. Let me see if we can show this properly. So probably you have to see it close. But there is one on top, one underneath, and one in between for the top of the bottom of one that is on the top of the other. Okay? So there's where we have the read-write heads. So I'm gonna put this in circulation and take a look, and then back and forth, back and forth.
Is that
Pardon?
is that SEC?
Is that the Shiba, I guess? No one? You say a what?
No, I was trying to figure out what type of one. Was it SETA?
I don't know.
It should say on the top.
Yeah. No, it's not the Shiba. It's okay. All right. When we get there, we'll see. Meanwhile, we're going to continue talking about the I/O procedure. The I/O procedure, we're going to be back there because we need to talk about the I/O queue. But let's review today the I/O system. Okay. So we know that there is ready. We know that there is a running. We know that we have wait I/O. And here we have a queue of requests. And let's say the device. In our case, it's a hard drive. Okay? So another way to look at this system is by saying, for instance, we have the ready queue, all the processes. We have a CPU, which is the running state. From CPU, we can go out of the system, right? If we go to end of program, or we can execute an I/O, which means that we can send it to the I/O. And then from here, we can go back to ready, because from wait I/O, we can go to ready, right? So this is another way to look at the system, as a system of queues connecting some servers. Oh, I forgot. Right here, we have the disk. All right. So we can look at the system that way. By the way, you should start reading chapter 12. we're teaching OS in the jumping style, not one chapter after the other. Chapter 12. Okay, so we have talked about the star I/O. We have talked about how the I/O request block is created using the producer-consumer. We're going to go back to that producer-consumer, but let's take a look to the I/O system. This is, let's say, the system where we have the application here, our programs, or where we interact with the computer, and down here we have all the resources. Okay, we have CD-ROM, hard disk, keyboard, controller for printer, and connection to a network. To send a message to a network is practically like initiating an I/O operation. So here you see that we have the application, then we have file system and virtual memory management. We will talk about that later. So if we need to read from a file, we call the file system, and the file system will communicate with the block-oriented device management, and this one will get to the device handler. You can see here, these are the device handlers. And then these are the controllers. So you can see that for each device at the bottom, there is a controller, which is that board we were talking about before. All right? And then there is a piece of software. Okay, this is the hardware-software interface. A piece of software which is the device handler. So we have a device handler for the CD-ROM, device handler for the hard drive, device handler for the keyboard, and so forth. So this is software, and this is hardware. On the hardware side, we have the media and the controller. Software side, we have device handlers and other blocks of the operating system. Okay? Here we have what we consider the I/O system in between, because file system and virtual memory management has to interact with the I/O system. Why? Because when we create a program is a file, an executable file. Or if we create a data file, we have to interact with the file system, but the file system has to interact with the I/O system to store this file in a persistent storage, like the hard drive. So that's why how the file system will be placing our files in the hard drive, for instance. In case of virtual memory, and you will see later, a quick view is that we can divide the program in several pieces, and then we have in memory just some of them. We call those pieces pages. And then the whole program is in the hard drive, but when we need one of the pages, then we can call it on demand. So the virtual memory management will execute an I/O operation and bring the page to through the application by placing the page in memory. Okay? So these two modules that we're going to study later interact with the I/O system. This part on top is what we call high-level subsystems. We call it subsystem because usually we have the operating system like a kernel where we have process management, for instance, interrupt handling and so forth, and then we have subsystem like file system, memory management, okay? And then down here we have low-level subsystems. So we go from the high level, as we were saying, the application communicate with some modules that they have to use the I/O system to get in touch or to use the low-level subsystem. Is that clear? Yes? No? Okay. Here, what is this that we have right here? I like it. The drivers, device handlers, device drivers, usually we call them. And this one? Controllers. This is a hardware piece, okay? And let me show you a better picture. Okay. Okay, this is the controller we were explaining last time. This is the case of the hard drive. So we have some circuitry here, or processor, even could be an Intel processor, that receives the commands from the device handler, the software, and this one is the interface that is going to communicate the device handler software with the media. Okay, so we send signal and we get data in this buffer, and we can send that back to the device handler. This is what we were talking about. This is the controller where we have the buffer, okay, and so this is the controller, and this is the device handler or driver. Okay. Here we have a controller, and we have several parts there. We have the opcode register. See, the driver is going to place information in the controller, and the controller is going to take some actions. So we have operand registers. So the driver can put information right here, right in. We have a busy register to check if the device is busy. The status register, the data buffer. Okay, read write. Because we can read. Imagine you have a hard drive. You can read from the hard drive this way, or you can write to the hard drive. Okay. So there are different ways to handle the I/O. Here, describe the operation which the driver wants the controller to carry out. So we're going to tell what is the command and some parameters that we need. This one indicates the controller is busy and that it cannot accept another request. So if the controller is busy, then that's the reason why if it is busy, we need to have this queue of, or this one is the same thing, of I/O requests waiting for using the disk. Then this one right here is called status register, indicates completed operations and report to the driver. You remember perhaps that when we have the producer consumer, we say, well, the device handler initiate the physical operation, right? And then, let me show you. So, initiate I/O. And then, when the I/O operation was completed, you have operation complete to the device handler, right? Okay. Indicates operation complete. So when the I/O operation has been completed, the status register knows it, and that information is sent to the device handler. And this is the data buffer. We're going to put their data if we would like to write it into the disk, or we can get data from that buffer. The buffer is memory. Oh my God. From memory, if we need to read in from the device, we can take this and send it to memory from the device, which will read the data, and then from here we put it in memory. Or we can write to the hard drive by placing the information here and then copying this information to the device. Okay. So there are different ways for the OS to handle these controllers or handling I/O. One is this. Do you remember? Perhaps in computer architecture, I don't know if you have taken, but in computer architecture, we had a small. When I teach it, we have a small assembly language, and then we have memory addresses. And for devices, we have just an identification of the device. Device 5, device 9, device 7, whatever. So this is one way that you can let's say consider the devices by saying this is the format of instruction. You can have an instruction like load from memory location. But also with this is the operation and this is the address. But we can use the same format to say in from device 5. Okay? So we're using the same instruction format and development of assembly language to, in this case, we're using an instruction that is going to access memory. In this case, we're using we can write here read if you like, if you wish. So here we're using the same format, but now this represents an input-output operation, and this is the device address, if you like. So this is what we're saying here. We have memory, so there are instructions that access memory and instructions that access devices. Okay? We say two different types of instructions used to access memory and devices. Well, in that one we can use the same format, but in the address field, we're just or we have a memory address or we have a device identifier. Another way to organize memory is that we just imagine that memory goes from 0 to 1000. Okay? And then location 1001 will be the address for this device. 1002, the other device. What is the conclusion of this one? That when we need to use a device to access memory and put the data in that location. And what it means is that we are initiating an I/O operation. So it's just like a global address space. So there are two ways that we can do this. Okay? Memory, or just all this as memory is an extension, and memory location N will be a buffer for a device. Okay, so different type of I/O interrupts. So we see there that we have a controller, and this one is called program input output with pooling. It means that we're going to initiate the I/O operation, and we're going to be testing the controller. Is the operation is it complete? Is it complete? Is it complete? So we can be pulling or testing several devices. Okay. So we have CPU, we have memory. So step one, we set up the register with all the parameters that we did there. Let's suppose that it's a hard drive. So we can say track 5, okay, sector 2, and then any other information we need. And then we can put here the operation. Okay. So we can say read, write. And then we set the PC register to PC, which means that this controller or that device is engaged in an I/O operation with a certain process. Then step 3, when we put the command here, the device and the controller start sort of conversation, and then if there is an error, we'll retry and so forth. So we start transferring data from the device to the buffer. Remember that a buffer is memory in the controller. Then, during the I/O operation, as you see here, the CPU is just testing this flag. Still busy, still busy, still busy, and so forth. And then, after the operation has been completed, the status register will indicate that the I/O operation is done. And then we can just take that information and transfer it to memory. We're doing that through the CPU, which means that if another process was running, in this case, and initiate an I/O operation, the OS stays controlled, but the OS has to be there just testing. So no other process is going to get the CPU, because the operating system is testing all the time. Not like we did before, that we initiate the I/O operation, right? And then we brought up another process to the processor, correct? In this case, the process initiate the I/O operation, and the OS keeps the CPU just testing. Okay. This one is the one that we have been talking about with the state diagrams. interrupts, I/O with interrupts. So you see that now we have more hardware in the controller. We have a control logic here. And the idea is that we're going to initiate the I/O operation, and when the operation is completed, then the controller can send a signal to the CPU saying, interrupt, operation complete. And then the interrupt routine gets there, and then the interrupt routine tells the handler, operation complete. You can take the data and put it in memory for that process. Okay, so this is the I/O operation that we have been dealing with from the beginning of the semester. So here, well, initially we set up the parameters that we need to handle the device. Then we send a command here, read, and the busy register becomes busy. And then we start transferring information, data from the device to the buffer. After that, we see operation complete, controller issues interrupt, running process suspended, and waiting process resumes. Okay, so what it says is operation is complete, controller interrupt, running process is suspended. Okay, the waiting process resume, but instead of resume, we could say waiting process goes to ready state, right? Because when we have the I/O interrupt, the process goes from waiting for I/O to ready. Are you following me so far? And then this is the interrupt signal we have been talking about. This is the I/O interrupt. Okay? So we have to call the routine. When we receive this, we have to call the routine to handle the interrupt. And then this routine is going to locate the device descriptor. Remember that in the device descriptor, we have the originating process. We're going to be back there. So this one signals the handler knows that the operation has been completed, and well, continues running. Okay, so we were here. And then, we're going to do number 5. Here we check the status, of course. If there are no errors, then we can transfer data from buffer into memory. But we're doing that through the CPU, which is a problem. Okay? Because the CPU is used by many processes, and in the early days it was that way. Also by the OS. So we're going to spend some time transferring data from CPU to memory. That's fast, but it's a time that we're consuming that can be used for other things. So there is another type of hardware which is called direct memory access. So there is we forgot, there is a connection from CPU and memory, of course, because, let me see, we can do something here. There is a connection there from okay, let me try. Okay, there is also a connection from CPU to memory. Oh, sorry, it's bidirectional. Because we load instruction, but we store as well. Yes?
Shouldn't the device have some sort of connection to at least the controller to tell it what areas of memory it can access?
The device?
Yeah. It's gonna so the controller itself is pushing to the main memory instead of whatever. So it should have an idea of where the actual like what memory blocks are allowed for that device.
Well, remember that the data comes into this buffer.
Yeah.
And we have to store this in memory. So when the data is here and the operation has been completed, we have the interrupt. When there is an interrupt, then who takes control? The I/O routine, the interrupt routine, the interrupt handler, correct? So if the interrupt handler takes control, then it means that we're going to run this routine. And this routine knows how to locate the descriptor. Why? Because we have originating process. So if we are giving service to this one, we have here a pointing to the process that initiated the I/O operation. So this information, we can copy that into, for instance, current I/O request block. Okay? Sorry. And then, or if this is appointed here, oh no, sorry, on top of it, this one, we can copy this operation, originating process, right here. When we select this one, and we're going to give service to this one, this information in the I/O request block is the one that we copy in the controller. We initiate the I/O operation. When we have the interrupt, we know the interrupt handler can locate the device descriptor, which is this one. And here, we copy from the I/O request block the originating process address right there. So we know how to, this is a pointer to the PCB of the process that initiated the I/O request. And pointing to that process, we know what is the memory. You know that the process has the PCB and the runtime environment, which is the data section, code section, heap, stack, and so forth. So once we locate the process, we have access to all that. So the OS can take the data and can put it in the memory area for that process. Okay? All right, so here we have, well, this is bidirectional because you store information in memory and load information from memory. Remember, there is a two-way, let's say, access from CPU to memory and from memory to CPU, both ways. Okay, so we initiate, we put the parameters here, taken from the I/O request block. Then we set the instructions here, read. For instance, set the flag busy so no one else can use it. The data transfer is initiated. Then, look at this. It says here, controller copies data between main memory and data buffer. If the controller is able to copy this data directly to memory, you know that the CPU is accessing memory all the time. Fetch, execute. Remember, fetch, get the instruction. Execute the instruction. But we can execute the instruction in the CPU without accessing memory. So, from these two devices, the I/O device and the CPU is the one that more frequently accesses the memory, right? That access memory. All the time, fetch. Every time we fetch an instruction, we're accessing memory. So, as this one is accessing memory, let's say 98% of the time, we can give a priority to the I/O device to access memory. We cannot access memory simultaneously. So we're going to allow the controller to access memory, and the CPU is going to wait for a millisecond, nanosecond, something like that. Okay? I'll let you know how we're going to do this. Okay, but then if we can transfer information directly to main memory, the CPU can be used to run another process. So with this model, we can do what we were explaining before, that a process was in running state, initiate an I/O operation. Another process can take the CPU. And then if the process completes the I/O operation, all right, we can, while we're doing the transfer, we don't have to use the CPU. The data is sent directly into a memory area. And then, of course, the OS will take the control of the CPU to do some management there, some handling, and change the state of the waiting process from waiting to rest. Okay, so there is an I/O interrupt, okay, and then the status
is red just to see if the operation was successful. Is that clear? This is the same thing that happens at the beginning with the CPU and the ready queue and all that. We're going to be talking about this, and little by little the pieces will be put together. But you got the idea of what we're doing? Okay. Now, how can we do, I'm going to talk a little bit about hardware today, but very little. How can we design a controller in order to handle this situation where the CPU is accessing memory all the time? We have to stop the CPU for a nanosecond, let's say, to allow the controller to access memory. And we're going to do that because CPU is accessing CPU all the time, the memory all the time, so we can take a couple of cycles. Okay? All right, to do that, let me show you this. A CPU works, is an automata, and it works as a clock. This is a clock. And the clock, what it does, is sends pulses. So what we have is a trend of pulses as 0, 1, 0, 1, 0, 1, 0, 1. Okay? At every pulse, which is a value 1, the CPU takes an action. For instance, when we did the fetch cycle, remember that we say program counter goes from program counter to memory address register. That's one clock tick. Next clock tick, from memory address register, we access memory. And we get into the memory data register. That's another clock tick. Next clock tick, we move it from the memory data register to the instruction register. So the fetch cycle was like 5 steps. Each one of them was a clock cycle, let's say. Okay? And for the execution of instruction, the same thing. So we have this clock sending clock ticks to the CPU, and the CPU is executing instructions. So the CPU, what it does is a sort of automata, it's an interpreter, it just executes instruction, nothing else. So the CPU is accessing memory all the time. So imagine that we have our controller for the DMA, and that we have a bit right here that the controller can set to 0 or 1. Let's say that the value is 1. Do you remember the AND gates? We need 2 1s to get a 1. So when the value of the clock tick is 1, as the controller bit is 1, so we have a 1 that passed through the gate. So all the 1s are passing, and the CPU is running. So when the controller needs to access memory to transfer information, it sets this 1 to 0. So if we put a 0 here, then there are no clock ticks that will pass through the gate, correct? And then what we're doing is called a cycle stealing. So we're going to steal a cycle to the CPU. So in that time, the CPU is, what it does is just wait a clock tick, a value 1. When it receives it, some action is taken. But the CPU doesn't know anything. Oh my goodness. The CPU is just waiting, and then he has to wait a little bit longer, but he doesn't know why. The CPU doesn't think. So it's waiting. For some reason, the signal has not arrived. It has to wait. So in that moment, in that cycle that we are stealing, the controller takes data on the buffer. Remember, from the device, we put it in a buffer in the controller, right? And we store it in memory. Okay? And then if we need another cycle, perhaps we do it later. But between one cycle and the other, perhaps the CPU has executed 100 programs. Okay? I mean the cycle is still not between one cycle and the next. So from this cycle we have stolen, and the next cycle that we steal later, perhaps the CPU has executed 100 programs. So stealing that cycle is not too much. Okay? So this is the way how the controller steals the cycle, access memory, and then could be accessing memory to copy from, because we're reading from the disk into memory, or we can access memory to take information from memory, to put it in the buffer, to write it in the hard drive. Okay? Is that clear how it works? All right. Good. Well, now that we have an idea of what is the I/O system, and we have an idea as well of how this ugly thing works, this algorithm, we know that the user initiate the I/O. This one assembles the I/O request block, insert that I/O request block in the I/O request queue, and the device handler is taking I/O request block, initiating operations. The controller handles the operation. When the controller sends the interrupt signal, the interrupt routine gets in, locate the device descriptor of that I/O operation, tell the device handler. The device handler can then use DMA or any other type of protocol that we're using just to get the information and give it to the program. Okay, that's the global idea of what we're saying. Now, we know that the DUIO is inserting I/O request blocks in the I/O request queue, right? And the device handler is consuming them, correct? All right. Information that we have in the I/O request block is required to use the controller. Because in that controller, you remember there was some register, right? The controller. So in that controller, we have let me go back. In this controller, we have this register here that if we, so we said if we're going to read, we have to tell which track, which sector. We have to give information about where in the hard drive we're going to read we're going to get the information. And then we send this command that says read, and then this is like a function. This is the name of the function, and these are the parameters that we're passing, okay? All right. So here we have information about the device, how many bytes are we going to transfer and so forth. One of these fields, let's say this, let's say is the track numbers. Another could be the sector numbers. So what is the track number? We have a hard drive as the one you have there. A hard drive is a series of concentric circles. Each one of these is called a track. And the data we're going to read in, or the area where we're going to write down on the hard drive, is on these tracks. So this disk is rotating. And the read-write head, the one that moves back and forth in the disk that you are just passing around, is somewhere, let's say here. If we need to read that information, the read-write head has to move from this track to this track. Right? And when this information goes on past, because it's rotating underneath the read-write head, the read-write head will read it. All right? So we're going to start talking on, I think it will be on Monday, but I will let you know a little bit today, about this scheduling. For this scheduling, we're going to make an abstraction of many things. We're going to focus just on the track number. But when we talk about the track number, you have to imagine, or you know implicitly that we're talking about the I/O request block. It's a request. Because we're saying there is a request to track number 5. There is a request. Let's suppose that we take a look to the I/O request queue. So we see the I/O request block, but we just look at the track number. The first one is to track 5. The second one to track 5,000. The third one is track 3. The other one is at track 4,000. So you see the read-write head will be back and forth, back and forth, back and forth. So what we have is a series of numbers here: 5, 100, 6, and so forth, which are the number of these tracks. Why do we need to know that? Because we can, taking the track number, create a scheduling algorithm, and look at this example. Imagine that I have the first request is here. The second one is right here. This is number 2. And the third one is right here. And they are, assuming that we have this, right? This is the track, this is number 1, number 2, and number 3. 1, 2, and 3. Okay, if we're applying the first come, first serve algorithm, the read-write head has to move this way, from here to here, and from here back. Imagine that the first is in track 1, the second is in track 5000, and the third one is in track 2. So the read-write head has to travel 5000 tracks from the outermost track to the innermost track, and then backwards, practically to the innermost, to the outermost track. So I have to travel roughly 10,000 tracks. Assuming that moving from one track to another is one time unit, we're talking about 10,000 time units. So instead of giving service 1, 2, and 3, we can have this scheduling algorithm that it says that we're going to give service 1, 3, 2. What does it happen? That we're going to do 1 first, this one from this track, then this one, and then this one. So we're going to travel half the distance. And then, depending on the scheduling algorithm that we're going to use, the average access time per request should be smaller. And when you read a catalog for a hard drive, you see average access time 10 milliseconds. Well, sometimes one request takes 20 milliseconds, another takes 30, but another takes 3. So on average is 10 milliseconds. Okay, but to have a very nice, an optimal average access time, we have to find a good scheduling algorithm. So there are several that we're going to study here. So the idea is this: assuming that we have a list of requests to different tracks in the hard drive, let's see how these different scheduling algorithms work to, let's say, optimize the average seek time. We're going to talk about seek time. We're going to talk about rotational time, let's say, transfer time. But we're going to focus in the average seek time because that's the one where the read-write head has to move from one place to another. So if we minimize those distances, then the average access seek time will be optimal. That's what we're going to do. All right? Any questions?
Back to the controller one, does that mean the controller could render the CPU useless if it never gave control back to it?
No, it has to give control back to it because the operating system, remember, is handling all the resources. So this is a mechanism because the one that's going to set that value to 1 is the operating system. Because the controller is hardware.
Yeah.
The device handler is part of the operating system. So when the operation says operation complete, it's an interrupt to the OS. Interrupt handler is OS. So that one says, well, I'm going to put this in one clock cycle and take it back to 0. Oh, sorry, 0 and then back to 1. Because it's the software in the OS who handles it.
Yeah, but I'm saying like if something went wrong though in the controller and it just stopped.
If something went wrong into the controller, the operating system has the mechanism to detect that something is happening there, and then the system could crash, for instance.
Yeah.
Or it can recover, and then we could say, well, this device cannot be accessed.
Okay.
Okay? That could happen. All right? Any other question? Well, have a very nice weekend. I'll see you Monday. Yeah. there is no class here, what is
Yeah, but I think the OS.
Yeah.